The lesson objective of this video, students use medians and altitudes of triangles to solve problems. So today we're going to be talking about two different special segments. The first one we're going to talk about is medians. The median of a triangle is a segment that goes from the vertex to the midpoint of the opposite side. So in my figure there, BC is a median. And so if BC is a median, then I know that AC would have to be congruent to DC. Because if it's a median, that means that C is the midpoint of AD. So just as we had concurrency with perpendicular bisectors and angle bisectors, with medians we also have concurrency. The point of concurrency for the medians is called the centroid. And it's actually the balancing point of the triangle. If we were to find the centroid of a triangle and balance it on our tip of our finger or the tip of a pencil, the triangle would be balanced. So there's a special relationship that happens when to the medians as they go to the centroid. If I look at BF, which is the median, BP turns out is twice as long as PF. So it takes 2 PFs to equal 1 BP. And then the same is true for the other ones also. If I look at AP here, it's going to be twice as long as PE. And CP is twice as long as DP. So in essence, what I've done is it's been split into thirds. 2 of the thirds are up here, and 1/3 is down below. So BP is actually 2/3 of the whole median, BF. And PF is just 1/3 of BF. So, and the same would be true for AE and CD as well. So you can look at it any way you want to, whether you use that the one piece is twice as long as the other piece, or if you use the 2/3 relationship, whichever way is easier for you, you can use. So in example 1 here, we've got the triangle, in triangle ABC, P is the centroid, and I'm given that BP is equal to 6. And I want to find PF and BF. Well, if it takes 2 of the PF, basically BP is twice as big as PF, I know that PF has to be 3. And so then the whole thing is just 6 plus 3, or 9. And if we look here, we're going to suppose that AP is equal to 10. So if that equals 10, PE is going to be half as much. So PE is going to equal 5. And then the whole thing, AE, is going to equal 15. Okay. Suppose instead of giving you just the piece, I tell you the whole thing. Suppose that CD is equal to 12. Can you figure out what CP and PD would equal? Think about it for a second. Pause the video if you have to. So if the whole thing is CD is 12, I have to cut it into 3 pieces. And the smaller piece, PD, is just one of the pieces, so that's the part that's going to equal 4. and then it takes twice, 2/3 of that, or twice as many to make CP. So CP would equal 8. So we can use this 2/3 relationship to find the point of concurrency on a coordinate grid. So the point of concurrency is we're given the vertices of a triangle, JKL. J is at 1, 2, right here. And K is at 4, 6, here. And L is at 7, 4. And I already had my sides drawn in there. Okay, so here's the triangle. Now, to find the medians, the median has to go from the vertice to the midpoint. So I have to find the midpoints of the sides. So if I find the midpoint of JK, I'm going to average my x's and average my y's. So for JK, I've got 1 plus 4 divided by 2, and 2 plus 6 divided by 2. And so that 1 plus 4 is 5 halves, so that's 2.5. And 2 plus 6 is 8 divided by 2, so that's 4. So 2.54 would be the midpoint of JK. So I'll go ahead and mark that. 2.5. There we go, right there. It's the midpoint of JK. To find the midpoint of KL, I'm going to do the same thing, average my x's and y's. So for KL, I've got 4 plus 7 divided by 2, and 6 plus 4 divided by 2. 4 plus 7 is 11, divided by 2, that's 5.5. And, excuse me, 6 plus 4 is 10, divided by 2 is 5. And so the midpoint of KL would be at 5.55, which is right here. Then finally I'm going to find the midpoint of JL. So I've got 1 plus 7 divided by 2, and 2 plus 4 divided by 2. So 8 divided by 2 is 4, and then 6 divided by 2 is 3. And that's right there. So now that I have the midpoints, I can draw the medians. So I have, I go from J to this midpoint, K to this midpoint, and L to this midpoint, and I see that where they intersect, the centroid, is at 4, 4. Well, it turns out there's actually a shortcut that you can use. Rather than going through all of that trouble, we can actually average all the x's and average all the y's. So that's one way of doing it. We can find it that way. Or we can take the shortcut, average the x's, average the y's. So we would just take all our x's, 1 plus 4 plus 7, and divide that by 3, and then all our y's, 2 plus 6 plus 4, divide that by 3, and so 1 plus 4 plus 7 is 12 over 3, and then 2 plus 6 plus 4 is also 12 over 3. And so you see we get the same point, 4, 4. Okay, now we're going to talk about altitudes. An altitude of a triangle is a segment that goes through the vertex and is perpendicular to the opposite side, or to a line containing the opposite side. So, for instance, this first triangle that I have, my altitude ends up being inside of the triangle. But when I have an obtuse triangle, like this second triangle here, two of my altitudes end up being outside of the triangle. So if you have an obtuse triangle, we end up with two altitudes outside. Because if I have my other altitude, if I continue this side out here, my other altitude would be out here. So we end up with two altitudes that are outside. And when we have a right triangle, so this is my right triangle here, I can draw an altitude this direction. That's one of my altitudes. But it turns out this is an altitude here, and this is an altitude here. So when we have a right triangle, the two legs are two of the altitudes. So similar to all the other special segments we've been dealing with, altitudes of a triangle are also concurrent. So the lines containing the altitudes of a triangle are concurrent. And the point, what we call the point of concurrency for altitudes, is the orthocenter. So when we have an acute triangle like this one, then the orthocenter is inside of the triangle. Okay, so for these next two, we're going to find the orthocenter, or the point of concurrency of the altitudes. So with my first one, A, I've got a right triangle. So this is an altitude, and this is an altitude. My legs are the altitudes, and then my third altitude goes to the other side. So where the point of concurrency is right here on the corner. So whenever we have a right triangle, the orthocenter is actually on the triangle. Example B, I have an obtuse triangle. And like we mentioned, for our obtuse triangle, two of the altitudes end up being outside of the triangle. So the one that's inside, that's not too hard to find right there. But the ones that are outside, I have to extend the side out here and find the altitude. And I have to extend this side also. Since my altitudes are actually outside of the triangle, I have to extend those lines until I find the point of concurrency. And then we find, there it is, right there. So in this case, the orthocenter is outside the triangle. Isosceles triangles. Well, it turns out when you have an isosceles triangle, the perpendicular bisector, the angle bisector, the median, and the altitude from the vertex to the base are all the same segment. Because first of all, if I just tell you that this is a perpendicular bisector, well, if it's a perpendicular bisector, then the segment, the base, is bisected, so those two pieces are congruent. And I would know by reflexive that this is congruent to itself. I have congruent triangles because of the right angles also. This would also be a right angle. So by side angle side, I know those triangles are congruent. Well, that means that these angles are congruent. So that means it's also an angle bisector. And because it's going from the vertex to the midpoint, it's a median. And because it's going from the vertex and it's perpendicular, it's an altitude. So this segment is all four of them. It's a perpendicular bisector, an angle bisector, a median, and an altitude. Now that's only true on an isosceles triangle of the segment that goes from the vertex to the base. It's not true of the other two segments that go to the legs. With an isosceles, or equilateral triangle rather, though, now all of the segments have that same property. In an equilateral triangle, the perpendicular bisector, the angle bisector, the median, and the altitude from any vertex are the same segment. So looking at my red line here, it's going to the midpoint and it's perpendicular. And so then these angles are congruent. So all of those are true. It's an angle bisector, it's a perpendicular bisector, it's a median and an altitude. And then I have the same thing over here. Now my sides are all congruent, so all my angles are also congruent. So all the pieces of the sides are congruent. All of the pieces of the angles are congruent to each other. And then all of these would be right angles. And so because I know in an equilateral triangle, the angles are all equal to 60. And so that means that when the angle is cut in half, that part of the angle will be 30 degrees. So we're going to actually prove that the altitude to the base of an isosceles triangle is also the median. So what we're given is that triangle ABC is isosceles with base AC, and BD is an altitude to the base AC, and we're going to prove BD is a median. Well, in order to be a median, that means it has to be going to the midpoint. So I'm going to have to show that AD is congruent to CD. Well, before I can say that those are congruent, I'm going to have to show that the triangles are congruent. So that's the first thing we're going to work on. So if it's an isosceles triangle, by definition, then the legs are congruent. So I know that AB is congruent to CB because of the definition of isosceles triangle. And then the base angles theorem tells me that angle A is congruent to angle C. Now, I told you that it was an altitude, and so because it's an altitude, that means that it has to be making right angles. It has to be perpendicular. So I know that BD has to be perpendicular to AC, since I said it was an altitude. That's the definition of an altitude. If they're perpendicular, then they're making right angles. So angle ADB and angle CDB are right angles. because perpendicular lines form 4 right angles. And therefore, because they are both right angles, I know they're congruent to each other. So angle ADB is congruent to angle CDB because all right angles are congruent. So now I have enough. I've got my side here, I've got an angle here, and I've got an angle here. So by angle, angle, side, I can say that triangle ADB is congruent to triangle CDB. And if my triangles are congruent, then all the corresponding parts are congruent. And so remember, we were trying to show that BD was a median, so the ones that I want to be congruent are down here. Now that I've said the triangles are congruent, I can say those two segments are congruent by CP/CTC. So for step 8, AD is congruent to CD by CP/CTC. And if those two are congruent, that means that D is the midpoint. Oops. Of AC. That's what it means to be a midpoint, the definition of midpoint. So now I've said that D is the midpoint, and so that's all I need to say in order to be able to conclude that BD is the median, because it's going from the vertex to the midpoint. By the definition of median. That concludes this video. Thank you for watching.